Hi, I'm Oromita and I'll be presenting our work. While we speak, our articulatory gestures overlap, which causes acoustic variation. In a VCV sequence, the features of each vowel affects the production of the other. So on the perception end, the listener must compensate for this in order to maintain salience in these categories. But when this does not happen, the variation gets phonologized, and this leads to vowel harmony. Here, the feature of V1 is now perceived as being a part of the category V2. So this becomes a grammatical feature of the language. So we can expect that the directionality of vowel harmony in a language would be the same as the direction of coarticulatory propensity that was there before vowel harmony developed. Given this relationship between the processes, we are interested in what happens synchronically within a system where this has already happened. And we'll look at such a system here. This is the vowel system of Khalkha Mongolian. There are 7 monophthongs, and this is an ATR harmony system. So vowels in non-compound words must have the same value for this feature. The directionality of harmony here is from left to right. So the features of the initial vowel determine those of the later ones. The high front vowel E is transparent. So when it is in a non-initial position, it does not participate in vowel harmony, which gives us what we are calling non-harmonic VCV sequences. Given what we know about how these vowel harmony system develops, we have 2 questions here. First, how does coarticulation function in a system where vowel harmony has already been established? And second, what explains the development of these non-harmonic sequences that we talked about? This relates to a broader question of how automatic speech processes interact with what we understand as abstract grammar. So in this study, we want to quantify the patterns of coarticulation in Khalkha Mongolian and then see how these compare between harmonic and non-harmonic sequences. Our data consists of speech that was read by 14 native speakers and covers all of the vowels in both initial and non-initial positions. So these are disyllabic words with a VCV structure, and we want to look at coarticulation between V1 and V2. When this V2 slot has a high front vowel, this gives us a non-harmonic sequence. For analysis, we extracted F1 and F2 at vowel midpoints. Plotting the F1, F2 vowel spaces for the initial and non-initial vowels, we see that for harmonic sequences, the V2 space is much more diffuse than V1, which suggests that there is greater acoustic variability here due to coarticulation. Comparing between the groups, V2 doesn't tell us much because these vowels have a complementary distribution. But when we look at V1, we see that the low front vowel A and the high back vowel U are both more diffused when they appear in the initial position of a non-harmonic word compared to harmonic words. So this suggests that there is some coarticulatory difference between these subsets, and we look into this in our statistical analysis. We know that the formant frequency of any segment should be predicted by the vowel identity. Here, to quantify coarticulation, we used mixed effects models to ask how well this formant frequency is explained by the identity of the other vowel in the word. And we also want to see whether there are differences in this tendency between the harmonic and non-harmonic subsets. So to compare the extent of coarticulation, we calculated effect sizes for the explanatory variable in each model. We can see here that for F1, coarticulation is robust in both directions. For both harmonic and non-harmonic sequences, the left to right carryover coarticulation is greater, which matches the direction of vowel harmony. When we look at F2, which is an acoustic correlate for the ATR feature, we see that harmonic sequences only show carryover coarticulation. In contrast, non-harmonic sequences show a greater coarticulation in the anticipatory direction. So this is from right to left, which is opposite to that of vowel harmony. We mentioned before that in the non-harmonic sequences, we can only have one category in the V2 position, which is the high front vowel. So these patterns suggest that this category has very high coarticulatory resistance. To summarize, we see that the patterns of coarticulation differ. In F2, the features of V2 are enhanced in the non-harmonic sequences. And the high front vowel, which does not participate in vowel harmony, shows very high coarticulatory resistance, which gives us some clue about how these sequences might have developed as non-harmonic diachronically. It's also interesting to see that co-articulation, which we generally understand to be inimical to contrast, could be possibly preserving or even enhancing contrast in a system where the overall tendency is towards feature sharing, and so the loss of contrast. Together, these findings suggest that automatic physiological processes in speech are not independent of abstract grammatical knowledge and vice versa. This is a work in progress. So one thing that we want to do is to look at explicit measurements of coarticulatory resistance using the locus equation framework. It would also be interesting to look at these patterns across a range of vowel harmony systems, which differ in the directionality of harmony, to see if we could come up with a typology. All of our data and code are available on GitHub, and also the model that we trained for this study. These are our references. Thank you.